In a forest in the eastern United States, the ground is silent for years. Then, on one warm night, it erupts. Billions of insects claw their way out of the soil at the same time, in numbers so vast they can be seen from space. They climb the trees, they scream a deafening mating song, they breed, and within a few weeks, they are all dead. And then the forest goes quiet again, for exactly 13 years, or exactly 17. Not 12, not 14, not 16. Always 13 or 17. And here's the thing that has fascinated mathematicians for decades. 13 and 17 are both prime numbers, numbers divisible only by 1 and themselves. These creatures, with no brain to speak of and no idea what a number even is, appear to be counting in primes. This is one of the most beautiful collisions of biology and pure mathematics in all of nature, and the reason behind it is a genuine survival strategy, sharpened over millions of years. The insects are called periodical cicadas, and they are unlike almost anything else alive. A newborn cicada drops from a tree, burrows into the earth, and latches onto a root. And there it stays, in the dark, drinking sap, for 13 or 17 years. It does not hibernate. It is awake the entire time, slowly growing, counting the years by sensing the trees above it pulling sap differently with each passing spring. Then, when the count is complete, an entire generation emerges in near-perfect unison. The densities are staggering. Over 1 million cicadas can pack into a single acre. For a few weeks, the forest is a wall of sound and motion. They have no stingers, no venom, no defenses at all. They are slow, clumsy, and delicious, and every predator in the forest feasts. And yet, somehow, the species survives in overwhelming numbers. The secret is not in how they fight back. The secret is in the timing, in those strange prime numbers. So let's sharpen the puzzle, because it is stranger than it first appears. It is not surprising that an animal might have a long life cycle. What is surprising is the specific numbers. Across all the periodical cicada populations on Earth, the cycle is always 13 years or 17 years. We never find a 12-year cicada, never 14, 15, 16, or 18. Just the 2 primes. Now 12 would seem like a far more natural number for biology. It divides evenly by 2, 3, 4, and 6. 16 is a clean power of 2. So why would evolution, over millions of years, throw away all of those tidy, convenient numbers and lock itself onto the 2 awkward primes sitting between them? The answer is that those convenient numbers are exactly the problem. The very thing that makes 12 and 16 feel orderly is what makes them deadly for a cicada. To see why, we have to think about who is waiting for them. Imagine a predator, a bird, or a wasp, or a fungus, that also runs on a cycle, with its own population booming every few years. Say this predator peaks every 5 years. Now here is the danger for the cicada. If a cicada generation happens to emerge in the same year that the predator's peak, it gets devoured, and far fewer survive to breed. So the cicada wants to emerge in years when the predators are not booming, to dodge them as often as possible. Picture 2 gears turning, one for the cicada's life cycle, one for the predators. The question is how often the teeth line up. A cicada that emerged every 15 years facing a 5-year predator would collide with a predator boom every single time it came out, because 5 divides perfectly into 15. That is a catastrophe. But a cicada on a 17-year cycle, facing that same 5-year predator, only collides once every 85 years. 17 and 5 share no common factor, so their peaks almost never meet. The prime number is a mathematical cloak. It lets the cicada slip between the cycles of everything trying to eat it. And this is exactly why it has to be a prime, and not just any large number. The whole trick depends on sharing no common factors with a predator's cycle. A prime number, by definition, shares no factors with anything smaller than itself. So a prime cycle cicada is invisible to the rhythm of almost every predator at once. Those on 2-year cycles, 3, 4, 5, 6. It dodges them all for decades at a time. Compare that to a number like 16. 16 is divisible by 2, 4, and 8, so it lines up perfectly with predators on 2-year, 4-year, and 8-year cycles, again and again. 12 is even worse. It collides with cycles of 2, 3, 4, and 6. Every convenient, easily divisible number is a trap, because every factor it has is a door for a predator to synchronize with it. The primes 13 and 17 have the fewest doors of all. Over millions of generations, the cicadas that happened to drift toward prime-length cycles were eaten less often, and slowly, ruthlessly, evolution filtered out every cycle except the primes. There is a second piece to the puzzle, and it is just as elegant. Why 13 and 17 specifically, rather than other primes like 11 or 19? Part of the answer is about the cicadas staying coordinated with each other. Their survival strategy depends on overwhelming predators all at once. There is safety in those impossible numbers. But if 2 different broods, a 13-year and a 17-year, were to emerge in the same year and interbreed, their offspring might inherit a cycle somewhere in between, say, 15 years. That hybrid would emerge out of step with both parent broods, alone, in smaller numbers, an easy meal. So the broods are under enormous pressure to almost never coincide. And how often do a 13-year and a 17-year brood actually collide? Only once every 221 years, 13 times 17. 2 large primes keep the broods cleanly separated for centuries, protecting the synchrony that keeps them alive. Mathematics is not just hiding them from predators, it is holding the whole species together. Now, biologists still debate the finer details. Nature is rarely as clean as a proof, and there are competing theories about exactly how this evolved. But the core idea is hard to argue with. Prime numbers offer real, measurable protection, and the cicadas that found them outlived the ones that didn't. And to me, that is the genuinely staggering part. A cicada has no concept of multiplication. It has never factored a number or heard the word prime. And yet, through nothing but birth, death, and time, evolution stumbled onto a piece of number theory that humans would not formally describe until thousands of years into our own history. The deepest patterns of mathematics are not just things we invented to fill textbooks. They are woven into the living world, discovered again and again by creatures that will never know they solved anything. The cicadas were counting in primes for millions of years before there was anyone around to be impressed. This has been Actually Rendered, where we show you how things actually work. If this one surprised you, you know which button to press.